Good afternoon, everyone, and welcome to this UCL East Lunch Hour lecture. We're very pleased to have you all with us today. My name is John Mitchell, and I'm the Vice Dean Education in the UCL Faculty of Engineering. And I've been involved in the UCL East project for around 5 years now, both with the engineering projects and with some of the teaching programs that are going out there. As many of you will know, the UCL East campus is UCL's biggest expansion in its near 200-year history. Situated on the Queen Elizabeth Olympic Park, construction of the first buildings are now well underway and on schedule to open in 2022 and 2023. From the start, UCL East has aimed to be very interdisciplinary. It's bringing together academics, students, industry, and the local community to work together to solve some of the biggest challenges we face for the future. And of course, it's inevitable that amongst these, climate change is right there up there as one of our major challenges. And as a significant global concern, we must be aware that the transport sector is still heavily reliant on fossil fuels and their powering of industrial internal combustion engines. This is causing the emission of harmful pollutants and is a major factor in our climate change today. We're delighted to introduce this lunch hour lecture, and Dr. Mike Whiteley has joined us and has kindly agreed to give the lecture today. Mike previously worked in UCL's chemical engineering department, leading hydrogen fuel cell engineering activities, but he is now the Director of Strategic Alliances for UCL East, with the aim of aligning the two worlds of academia and industry through collaborations and investment opportunities. Michael has a strong academic background in electrified vehicle technologies and is celebrating a decade of activity in hydrogen and fuel cell technologies. And he remains actively involved in the research on this cutting-edge technologies, and particularly researching future clean energy technologies. So in today's talk, we'll hear about what UCL's Advanced Propulsion Lab has set out to do, tackling this global grand challenge head-on, working towards zero-emission transport. They are developing clean technologies to help reduce air pollution and mitigate negative impacts on the environment. If you have any questions at any time during this presentation, we'll be using Slido to take those questions. If you wish to log into sli.do and enter the code LHL2, you can post questions there and I'll pose them to Mike at the end of the talk. So please welcome Dr. Mike Whiteley.
Thank you, John. Thanks for that introduction. And thank you to you guys in the audience for taking some time to spend with us today for this lunch hour lecture. I really hope you enjoy it. So as Professor Mitchell was saying, I'm Mike Whiteley. I've been at UCL now for a few years, working different roles from, as was previously mentioned, small-scale fundamental research and development on fuel cell materials, all the way up to systems integration and then systems engineering projects, working with industry partners with the support of UK government. So the title of this presentation is How UCL is at the Vanguard of the Green Industrial Revolution. And this is all going to be tailored around the existing capabilities and work we do now at UCL and what we're building up to with the Advanced Propulsion Lab on the UCL East campus. So unfortunately, we're going to have to start on quite a somber note, but a very important one. And that's the realization that we are in a climate emergency. So as I mentioned, climate change is a big concern. And why is this important? Well, anthropogenic climate change, or these man-made climate change phenomenon, can be linked to rising temperatures and sea levels, but also extreme weather events. Not only the likelihood of occurrence, but the extremity of these, or the severity of these weather events, and also shifting wildlife, human populations, and habitats. And this is quite upsetting. That recently we've had to coin new terms such as climate refugees, where people are being displaced from where they live due to these climate change phenomena. And this is our future, and indeed this is our present, unless we do something now. So when we talk about climate change, generally we're talking about carbon emissions, so CO2 emissions, and these are increasing exponentially. So we can trace this back to ever since the Industrial Revolution and the exploitation of fossil fuels for growth. The biosphere has really struggled to maintain equilibrium, because we are on a very finely balanced planet, and we're knocking this balance out with our activities. So this is when we've been taking coal out of the ground and fossil fuels in terms of oil and natural gas, to fund development, which civilizations must develop, but unfortunately at the detriment of the globe. And I've mentioned some of the kind of the global level difficulties here, but there's also local air quality concerns. So some recent work by UCL has shown, that was in the news recently, that a drop-off in local air quality due to fossil fuels actually caused 8.7 million deaths around the world in 2018. And to put this into context, this is more than smoking tobacco or more than malaria, and costing the health service more than $2.9 trillion. So some of this data we can see here from California, Berkeley, shows that the globe is warming up, and we need to put the brakes on. So where my interest lies, both on a personal and professional level, is how we can make the biggest impact on climate change. And to look at how we can make the biggest impact, we need to look at the biggest emitters. So if we look at this data, the most up-to-date data I could find for this presentation in 2018, the UK's transport sector was the most significant contributor, with more than 120 million tonnes of CO2 equivalent. So we need to make a significant dent in that emissions profile. And when we talk about transport, this can be anything from personal transportation, so how you get around in your car or on public transport, all the way up to your international flights for your holiday in aviation, but also freight, so on the roads through heavy goods vehicles or in international shipping. And because of this big problem, because the government is signing up to these ideas of reducing emissions, the UK industrial strategy has 4 grand challenges, and one of those has been set as the future of mobility. Through the future of mobility, we're looking at exploring reducing emissions through new technologies such as lithium-ion batteries and hydrogen fuel cell technologies. And ultimately, we're trying to set the UK as a science superpower in these novel electrified technologies. So I think sometimes we can be quite critical that governments aren't doing enough, but I think we're in a good position in the UK where the government is getting behind these ideas. And we can see that in November 2020, just last year, the Prime Minister announced his 10-point plan for a green industrial revolution. And this is 10 pillars of activity that can help us reach net zero targets in 2050. And this shows that the eyes of the government are on this issue. So here I've picked out some quotes from the document that are specifically related to electrification of the transport sector. And some of this you might have heard of in the news recently. So there's the ban in 2030 of petrol and diesel cars. And this basically means that in 2030, it will be illegal to sell cars in the UK that are 100% powered by petrol or diesel internal combustion engines. And they must have some kind of significant hybridization. So plug-in vehicles will be still available and full hybrids, which is a great first step. And then a close target after that of 2035, every car sold in the UK must be 100% zero emissions, so have no internal combustion engine whatsoever. And some of you may think, well, this is a long way away, 2035, we've got lots of time, what's the worry? But if you know how the automotive industry works, if a car company, just pick any car manufacturer, is designing a new vehicle, it will take 5 years or more just to design their new latest model of a car that uses their conventional petrol and diesel engines, where they don't have to think about a new technology. But now they're going to have to think of what's the power source of the future, what's the propulsion system of the future, and do all this in a very short amount of time. To kind of kickstart and catalyse this activity, the government set out some initial funding in this 10-point plan. So they've committed £1 billion to support the electrification of UK vehicles and supply chains, which is great news. Not only the manufacture of these new vehicles, but also the components that go in them from the tier 1 suppliers. They've also said that they're going to invest £1.3 billion to accelerate rollout of charging infrastructure. Because if we have these new vehicles, we're going to have to be able to charge electric cars and refuel hydrogen fuel cell cars across the country to make them viable. And also to help with that, the plug-in grant subsidies are increased with over £500 million towards making them more accessible to purchase. So this all represents an overall initial investment of £2.8 billion. And I think what's important to know up until this point, and it would have been great if those slides were working initially, is there's a global crisis in terms of emissions and climate change. There's policy that's put in place and market drivers are now making companies rethink their strategies. And a lot of these companies, because of these timeframes that are coming up, are having to make big decisions and changing Some of them have made their market dominance based purely on petrol and diesel cars, and now they have to completely rethink their portfolio. Which means a lot of people on the back foot. But fortunately for us at UCL, we've been doing this for over a decade. So the electric revolution is upon us for the transport sector, but UCL is certainly at the forefront of this. We're not playing catch up. And that is what one of the driving reasons behind the creation of the Advanced Propulsion Lab, or the APL. So who are the APL? Based at UCL East, the APL represents a union of world-leading academics from across the Faculty of Engineering. So as you can see here, we have chemical, mechanical, and electrical engineers all coming together in this trifecta of excellence, bringing everything, all their expertise from their respective fields. And that's because to tackle these grand challenges, such as the future of mobility, we need this multidisciplinary and this interdepartmental approach. We can't use the conventional academic way of having these siloed structures. So when we created the APL and the vision behind it, we thought, what is the application of the future, be it a passenger car, a train, or whatever it is that needs these new technologies? What would it need? And obviously we need new power sources. So that's where we need these new engines that don't use fossil fuels and don't burn anything. So this is batteries, fuel cells, supercapacitors, and that's where the chemical engineers come in. And then machines and drives. How are we going to turn this electrochemical energy into useful work, how to propel a vehicle? And that's where the mechanical engineers come in with electric motors and electric powertrains. And then finally, with the electrical engineers, we're looking at power electronics. So how can we charge and discharge these systems? How can we monitor them, make them talk to each other? And that's where the power electronics is where the electrical engineers come into play. So ultimately, this is led by Professor Dan Brett, who is a chemical engineering professor, but he has support from a team from across the university. And these last 2 points, I think, are quite important. It's the work that the APL is doing on UCL's campus is heavily influenced by industry and government. We see that the work we need to do needs to have a commercial viability. It needs to be something that will be implemented and used by the general public for the benefit of society. And we are now working with some of these companies that I've just mentioned that are not struggling per se, but branching out into these new technologies and have to really invest their activities into these low carbon technologies. And obviously we talk to government as well to make sure that the policies are set in the right direction and we're reacting to the funding mechanisms and policy decisions that are made at the government level. And the final point, it wouldn't be UCL if it wasn't forward thinking and disruptive. So I hope that gives you the overall view of what the problem is and how we're trying to answer it. Now we'll do a bit of a deep dive into some of the technologies that we're currently researching and scaling up at the APL. And as mentioned previously, hydrogen fuel cell work it was my bread and butter. It's what this year is my 10th year looking into this research, which makes me feel old, but this is the stuff I get excited about. So we'll have a bit of a deep dive here, so strap your thinking cap on. I promise it won't get too technical. So how does a fuel cell work? It's good to understand that before we go any further. And this schematic here shows that a fuel cell has a hydrogen supply at one side and an oxygen supply at the other. And then inside, the magic electrochemistry happens. So there's no burning. It's a purely electrochemical energy conversion device. In the middle, you have an electrolyte membrane, which is a polymer. So it's a plastic material. And it kind of looks like cling film, if you didn't know what it was. Then what happens here is hydrogen comes in from a compressed gas tank. And if you think back to your school days, hydrogen is the most basic element and most abundant in the universe. It's just one proton and one electron. When this comes into a fuel cell and meets the catalyst area, the catalyst is there to facilitate the reaction. The proton is split from the electron, and the proton can travel through the membrane, which is fine, it can pass that through, but electrons and the gas can't get through the membrane. So the electron has to go around an external circuit, and this is where you get your power from, the electricity. In this instance, it's a light bulb, but in a car, it'd be an electric motor, in an aeroplane, it'd be a propeller. Whilst all this is happening, at the other side, oxygen just from the air that we breathe is passed over the other side of the fuel cell, meets another catalyst area, and then this is where the proton and the electron from the hydrogen side meet the oxygen molecule, and that's where we form H2O, which is just water. So at the point of use, a fuel cell only emits water vapor, which makes it a perfect green technology at the point of use. So what do we do at UCL now in terms of fuel cell research? Well, This is a fuel cell that you can see now. So this is the membrane material, this kind of cling film looking stuff. And then we spray on either side a catalyst material. And this is platinum nanoparticles suspended on a carbon sphere, which is a good way of thinking of this is you think of a black football and you've glued table tennis balls all the way around it. You've got an out of scale but representation of what a carbon sphere looks like with nanoparticles of platinum on. This is then suspended in something called an ionomer, and we spray this onto both sides of the membrane to make a fuel cell. So once we've made a fuel cell, it's interesting to note that one fuel cell, the image we saw, doesn't actually produce much more than 1 volt in the real world. So it's not really that much use on its own. So what we do here, this is an image of one of our researchers working on a fuel cell stack system. And this is how we get more power from a fuel cell. So we stack these up as same as slices of bread in a loaf to make more connections, and then that voltage that was more than 1. In this application, where there's 60 or 80 cells, you can get around 60 volts. And then when you multiply that by the high current that a fuel cell produces, you can then get, I think this one here is about 8 to 12 kilowatts in power. And that's enough to power everything in your home, from your TV, your lights, your kettle, electric shower, and that's how fuel cells could be used. So we also look at this stack design and build. So this is a CAD model from one of our students who's taken the fuel cell material, this black area here, and thought about how can we optimize making a fuel cell stack itself, the kind of the more global systems engineering level rather than the materials level, and looking at optimizing how do we get the gases in and out, how do we get cooling in, how do we optimize all the fixtures, and that kind of work is what we're quite well versed in. And this goes all the way up to systems integration, and this is an example of automotive systems integration. But this is when the BBC came to talk to us recently about the work we do in fuel cell development. And as you can see in the middle, we've got an exploded system, metaphorically obviously, of a fuel cell. And here we can look at scaling and optimizing the balance of plant. So this is the air compressors that are pushing air into the fuel cell, the hydrogen recirculation system, the coolant. All of these subsystems that still aren't fully understood, we can tackle at the Bloomsbury campus now. So once we've gone from the materials level and built the optimized fuel cell, put it in an application, run it in a system, we also need to look at diagnostics and prognosis. So was the fuel cell running at its best? Did it degrade too quickly? Was it in the right environment? And what we do here is a lot of work with X-ray CT. So this is a X-ray scan of a fuel cell. So this is a very small segmentation. I think it's about 0.5 millimeter cubed. And this just shows that we can look after we've used the fuel cell non-destructively at the membrane material. Did this crack? Did it get thinner over time? Was the catalyst that we applied, did that move around or delaminate? And then this here is the gas diffusion layer, which is normally a carbon paper. And this is how you blow gas over one side and it diffuses through the fibers to meet the active area. Did this crack? Was this over compressed? And this feeds the next generation or the next iteration design for the fuel cell of the future. So to stay with that thought process and CT, I'm going to give a bit more detail of the recent work that we've done with CT and a recent paper that we published. So these next two slides with Homer Simpson, they're brilliant. They were kindly given to me by Dr. Francesco Iacovello, who's in UCL. He's the X-ray guru. And this explains the process that we use. And some of you might have come across this before, where you've heard of CAT scans or CT scans for internal medicine concerns. And it's used in the medical field a lot. And it's the premise of using a radiation source, like an X-ray tube, passing through a patient in this case. And then at the detector side, you can see what's happening inside. And we use the same thing to look at what's happening inside batteries and fuel cells and supercapacitors. But the CT part, so that's the radiography, that's one picture that you normally use for looking at broken bones. But the CT aspect is if you can take one image, rotate the object or patient, take another image and do this through 360 degrees, you start to build up a lot more data. Now, in a medical context, the patient normally lies on a machine still, and then the machine goes around them. We do the same, but in reverse. So we have the machine staying still, and then we rotate the fuel cell or battery. So once you've taken all these images, you've got all this data, quite a lot of data. We can then use machine learning techniques to reconstruct all these images in computer environment. And then we have two different ways of looking at this data. So the top section here is something called tomographic cross sections. So this is where you can look at slice by slice through the thing you scanned, looking at the internals and seeing what's happening. And at the bottom here, we can also stack these all up effectively and build a 3D volume rendering. And that's what you saw previously for a fuel cell. So I'm going to go on to a paper that we recently published looking at exactly those techniques for fuel cell research. And what we have here is we were looking at using novel materials for fuel cells to make them last longer, operate better, get more power out of them. And this material here is a metal foam. Quite self-explanatory. It's a foam, like a sponge kind of material, but made of metal. This is nickel metal, as it happens. And what we're looking at is how you compress this material. How does it affect performance? So here we have a side-on view of various levels of compression. This is a CT scan, and this is from a top-down view of the same material. So once we scan the material, once we've crushed the material in the lab, put it through the CT machine, and we've got this digital model, we can start doing some analysis, such as the pore density. So this is where we can look inside a material, what the void structures are like, how big are they, what's the average void volume. And as you can see, it's not groundbreaking in itself, but the more you crush this metal foam, the smaller the pores. But it's what we do with this data. So if we want to look at how fuel cells operate, such as gases in and out, water in and out, we can do things like computational fluid dynamics, or CFD. So this is a technique where you can use the model that we scanned in a digital domain to model how fluids, so it could be a gas or a liquid, flow through your material. And as you can see in this application, the more you crush the metal foam, the faster the gases go through. Which sounds great, because that means you get more gases going through, you get a higher rate of reaction, more power. Well, yes, but it's at a trade-off, because we also did some pressure drop analysis, which showed the more you crush this material, the harder you have to actually force those gases through, because of these Venturi effects where you get the speed up of gas. So that means, yeah, you do get more performance out of the cell, but then your balance of plant systems, like the air compressor, has to fight a lot harder to push these gases through. So there's this fine balance to be had in fuel cell systems engineering. So to marry with the in-house CT capability, we also use a technique called Neutron Beam Radiography with our partner institutions internationally. So this is a similar principle. It's imaging of electrochemical devices, but on a much higher energy level. So this is a representation of the facility we use in Germany. We recently took a group of researchers to this nuclear reactor. You have to be at a nuclear power station. And then we tap off a supply of neutron beams, these high energy beams, that can pass through your object of interest. So ours is a fuel cell or a battery. And the great thing with this is it's such high power, there's such high energy, that they don't really interact much with the metals. So you can put an entire fuel cell in there, an entire battery pack, and the neutrons will only really interact with the water molecules. And because fuel cells make water, we want to see where they make water. Are they making too much of it? So this is a perfect technique to use for fuel cells. So with this work, you see two images here. On the left-hand side, this is a conventional fuel cell flow field plate. So this is where we bring hydrogen into the fuel cell, and it has to snake along these serpentine channels, and that's how we distribute gas to the fuel cell itself. But what we were looking at on this right-hand side image is, can we use a different material? Can we simplify this? And can we just use a blank plate, but put metal foam on, and then the metal foam will distribute the gas and then bring the water out of the fuel cell system? It will reduce machining costs and possibly increase performance. So what we did here is we had a conventional flow field on one side and metal foam on the other, and operated a fuel cell in the nuclear facility in just on the outskirts of Berlin. And these are the results we got. So the blue areas and the yellow are areas of water accumulation. Fuel cells, when they operate, make water. So that's a great kind of a way of us monitoring how well the fuel cell's doing. And what we can see here is, when there's not much compression in a metal foam, there's actually quite a lot of water accumulation on the hydrogen side, and a few specks, kind of quite a lot of accumulation in the foam on the oxygen side or the air side. And what we can take from just looking at these images is the more you compress the fuel cell, the less water accumulated, which means there's less flooding, which means there's more reaction happening. So that sounds great. But again, we have to think of why we're seeing this, and there's a balance to be had. The more you compress this metal foam, the smaller the voids are, the less likely you are to have these reactions occurring in the electrochemical surface area. So we need to make sure that we get this compression of the foam correct. So if you've got any more questions on that kind of work and you're interested to hear more about the fuel cell, the novel fuel cell work we're doing, the link to the paper is there, and feel free to get in touch. But that is the small scale. That is from the nanoscale up to the single cell work. But as I mentioned, we also do systems work and industry-facing work. And this just shows a recent interaction we had. We were approached by Hyundai to launch their new fuel cell car, the Nexo. And through this project, we wanted to show that fuel cell cars during operation don't emit nasty particles. But interestingly, fuel cells, because they have an air feed, they need to have an air filter. So what we were trying to show with this experiment was fuel cells, when you use them, don't only not emit carbon emissions, but they actually clean up as you drive because of this filtration system. So what we did is we looked at these numbers here, which are PM 2.5 and PM 10. And that's basically particulate matter that measures 2.5 microns or 10 microns in diameter. And these are the emissions that you get in local areas that are severely damaging to health. And the reason why quite a few streets in London are over the limit set by the World Health Organization for these particulates. So what we did here, this is me before lockdown, before the beard, putting in PM 2.5 and PM 10 into this big ball. And almost like a dirty crystal maze, we had this carbon-infused sphere at the front of the vehicle. And when we ran the car, it consumed the cloud of soot at the start, and then at the back of the vehicle, it emitted just water vapor and clean air. And we used this as a bit of a press opportunity. The Hyundai representative unzipped the balloon at the back and got inside and showed that it was all clean air. So this next section is, so that hydrogen fuel cells is my bread and butter, as we've mentioned, so I've done a bit of detail on that. But I should also mention the work we do with batteries, which we do quite a significant amount on. And the principles are quite similar. They're electrochemical devices. They have anodes and cathodes and separators. It's very similar. But where they differ is fuel cells have to have a constant stream of hydrogen in one side and air in the other to keep producing electricity, whereas a battery has everything contained within. It doesn't need a fuel. Everything's within the cell. And what they do is they wrap these anode and cathodes and separators, and they wrap them up into this roll in a canister, which of some batteries you might have seen, or in a pouch. But basically, it's the same kind of functionality. But the work we do with batteries, just to take a snapshot, is the same as fuel cells from small level to big scale. And this is some examples of the work we do with battery safety. So these are some examples of where batteries have gone wrong. And unfortunately, because all of the reactants are stored within a battery, which is great in some instances, but in some safety concerns, it's quite severe. So if you think back to your school days again, this is the last time I'll ask you to do that. The fire triangle, everything you need for a fire is an ignition source, a oxidant, and a fuel. All of that is within the battery. So even if you think, such as NASA here, so we work with NASA on some projects for battery safety. If they want to send batteries up onto the space station or into space, you'd think, well, you can't have a fire in space, there's a vacuum. But because everything's contained within a battery for a fire, you can still have problems up there. So this is some of the work we do on battery safety. This is a thermal imaging video of a battery going into something called thermal runaway. And it's one of the main ways that batteries fail spectacularly, is that there's some kind of problem in the cell. It's been abused, it's not been produced correctly, there's too much heat in it, and this propagates and propagates until you get this kind of violent explosion. And this video looks pretty cool, it's great, but how much data can we get out of this experiment? We married this up with high-speed radiography. So this is the same battery as the one in the top there, and this is slowed down to, I think, around 30 times, showing that as you get these degradation mechanisms in a battery, and as the materials start breaking down, you get short-circuiting, the temperature increases, and this propagates and propagates. until ultimately, in the space of 1 second, this video is in real time, you get this violent eruption. And this is not what we want. So this, again, is how we use some of our CT capability that we have in-house to look at what happens inside batteries and fuel cells. So we have 3 different scales. We have a macro CT machine that can go down to 8 microns in resolution. And this is where we can put an entire battery or an entire fuel cell into the machine and have a look inside. If we want to go into a bit more detail, we have micro CT machines. So this is where we can look at a resolution of 0.36 microns. And here we can look at individual layers, so an anode and a cathode or the separator, and have a look at what's happening on those levels. But if we want to go crazy, we can go down to the nanoscale CT machine. And this has a pixel resolution of 63 nanometers. Now, to put that into some kind of context, that's about a third of the width of the human hair. And this is where we can see on a very, very tiny scale what's happening with individual bits of a sphere of carbon or a catalyst material. So as I mentioned with fuel cells, we do work from the fundamental level to more higher systems levels. And this is an example of some work by one of our promising researchers, Robert Mather, and he's working on looking at battery management systems. So trying to operate batteries in a way that we can avoid those spectacular failures. And some of the work that we do here is relating to these batteries called 18650s, and that's just a designation of how big it is. But this is a very common battery. And if you think of a Tesla electric car, they actually have up to 7,000 of these individual batteries linked up underneath the car. And obviously you don't want one of those going wrong because they have this chain reaction that would take them all out. So in an ideal world, you'd put a temperature sensor and a voltage and a current sensor on each cell, so you know exactly what's happening all across the pack. But unfortunately, you can't really do that because of cost concerns and the amount of space you have in the system. But what this research has been looking into is looking at these little Hall sensors. So very inexpensive sensors that can be picked up for a matter of pence. And he's integrated these into a PCB, so a printed circuit board, and then we can have an individual map of voltage, current, and temperature across each cell this is a module, but if you scale that up to a pack, you could do it across the pack. And this gives us a lot of data to show what's happening inside. And we've verified this with thermal imaging. So we can say, oh, it looks like through using our new BMS, cell 8 is doing a lot more work than cell 1. And then when we actually look at this from a thermal camera, we can see that there's a lot more heat in one side than the other. And how can we stop that? Because that means the hot cells are going to degrade quicker than the other cells and kind of make the battery pack of the future a bit more optimized. So we verify this in a variety of ways, but we also are pioneering some ultrasonic imaging techniques. So again, if we draw a parallel to the medical world, if you've ever been involved in a pregnancy, you'll know that you can use ultrasonic sensors to see inside in a non-destructive, thankfully, manner. And we're looking at using the same techniques for batteries and fuel cells. So if you could slap on a ultrasound sensor on the side of a battery, ping a sound wave through, it will interact with all those layers as it goes through and propagates. And then you can see, are these layers increasing in size over use? Are we getting gassing? This is a way to look at degradation. Or are they getting too close and they could short circuit? So we're looking at pioneering these new techniques using conventional equipment, but repurposing them to look at these technologies of the future. So just to give you an idea of scale of the team so far, the APL, like I mentioned, was made up of 3 departments, but then this is the representation from the chem eng side. So as you can see, there's a large group working on batteries, fuel cells, supercapacitors. We are at saturation point now on the Bloomsbury campus. We've filled the labs with people and equipment, and thankfully that's why the Advanced Propulsion Lab's a great opportunity. But also this slide shows that we're actually the first university to receive a fuel cell vehicle working with our partners in Toyota. So we use this here, which is a first generation hydrogen fuel cell car. And we go to green festivals and schools and whatever opportunity we can have to get this out there and show people that these new cars aren't scary, they're not much different, they feel the same, if not smoother. So we use this as an educational tool. As I was saying, we're growing, we're expanding. The work we can do now in Bloomsbury is restricted to a lower TRL, or technology readiness level, because battery packs, large battery packs like 7,000 batteries in a Tesla or a fuel cell stack that's very large, about the size of a filing cabinet, we can't actually do now in Bloomsbury. The electrochemical side of the APL is already more than 90 researchers strong, which represents more than 400 papers published in leading academic journals, which is representative of more than 7,000 citations. And interestingly, over £40 million of funding has been realised through the Electrochemical Storage Group since 2011. And just to show our industry acumen, we've also had 2 companies spin out with new technologies that we've developed in the labs who are doing really well. So as I mentioned, we're growing. The need for this kind of technologies from the government level and industry level, the interest we have is growing, but we don't quite have the space in Bloomsbury. So that's why, fortunately, the APL was selected as one of the entities to go out to UCL East, the new expansion project. And here we can see the architectural model for the campus site itself. So the APL is going to be occupying the 8th floor, a wing of the 8th floor of the Marshgate building, which is coming out of the ground now. You can go on the UCL East website and see some cool pictures of the skeleton of the buildings up. And the APL is going to have around 1,000 square meters of space to look at teaching and R&D, accelerating the technology readiness level from the lower levels, which will stay in Bloomsbury and carry on and keep prospering. But then we can scale up and do big battery packs, big systems, big electric motors, putting these into actual vehicles. And the important thing about this is this gives us more of an opportunity to work with industry on these higher TRL technologies. So we can talk to companies who are looking at hybridizing their fleets, or they want to develop a new technology to decarbonize an application that they have. This is exactly the kind of work we're looking into. And in fact, my daily role now is to talk to companies and government about how we can forge these partnerships for this mutual benefit. But interestingly, we've had some good discussions recently about extending the APL's activities to a hydrogen hub for London. And this is because we're in such a great position on the East Campus to benefit from the local waterways. So can we look at using these to test marine applications, or even ship in hydrogen that's been generated by the wind turbines on the East Coast into London? But also looking at having a hydrogen refueling station on site. So here we're looking at being able to implement a vehicle fleet or have hydrogen buses running around campus and having a place for those to refuel. And the interesting thing about the difference between fuel cells and batteries is that fuel cell vehicles can be refueled in the same amount of time to refuel a petrol or diesel car and then go back out, whereas an electric vehicle, a battery electric vehicle, would have to charge for it a lot longer. However, we will complement the fueling station with electric vehicle charge points across campus. But another opportunity we have is to use the local roads, footpaths, and local area to test personal mobility devices or disability mobility devices. So here we'll work with our partners in the Global Disability Innovation Hub. This is another entity at UCL East, or looking at, say, for example, e-scooters of the future, fuel cells and battery powered, or testing technologies within the campus. And I think that's an important point to make of the opportunity we have at UCL East for APL. It's bringing these technologies up to the next level, up to the industry-facing level, and working with key partners who want to invest in these areas and kind of react to what's happening in the industry because of these main drivers to change to an electrified solution, and working with them to develop these technologies and test them in a living lab concept. So how can we make a difference at UCL? Well, I hope I've made it clear that there is a global concern. There's a big issue with climate change. The United Nations Sustainable Development Goals have shown the key areas that the United Nations are interested in. And these directly influence things like the UK government's industrial strategy. So this is where they are looking to develop these 4 grand challenges. With the grand challenges, the main 2 that are related to the APL is the future of mobility, obviously, which is the main one, and clean growth. And where we can help as UCL is, like I mentioned previously, we are not on the back foot with this technology change. We've been doing this for over a decade. We are very well versed in these technologies, and we work with industry partners across the globe to develop these. And these industries are now changing with support of government. It's all coming together to show that UCL could be at the forefront of this green industrial revolution and benefit from being one of the leading lights in this development of electrification. So I hope that was interesting. It was a brief snapshot into what we're into, the work we're doing at UCL currently and what we're going to be doing. If you have any questions about the APL itself, the academic director is Dan Brett, or if you want to talk to me about anything that I've spoken about today, that's my contact email address. But for now, I'm interested in welcoming some of your questions.
Thank you very much, Mike. Perhaps, if people would like to post questions, the Slido service is available. So sli.do will take you there, and LHL2 is the code you need to enter to access this board. But maybe I could start. You talked about two main technologies, fuel cells and batteries, as some of the key things that you're working on. How do you see one coming out on top, or a mix? How do you see that playing out?
Well, it's an interesting question in terms of the industry over the past few years has been split between these two thought processes. But in reality, it's actually a combination of the two. There's no silver bullet to the electrification of the transport industry. Some applications will suit battery electric vehicles more so than they would hydrogen, and vice versa. So if you think of a small city car, a little two-seater smart car that's only doing short distances in a city, battery electric just makes more sense for that. I wouldn't suggest we start putting fuel cell into those just yet. But then on the flip side, if you have bigger SUVs or longer ranges or heavy goods vehicles or buses that require quick refueling and then longer duty cycles, fuel cells would suit the application more. But even so, fuel cell systems always have batteries inside them. So you have to make use of regenerative braking. So there's always a small battery pack in a fuel cell system anyway. I think a lot of people in the past have pitted the two technologies against each other and saying which force are you going to back. And that's probably because of people like Elon Musk, who owns a big company that does battery vehicles, saying that fuel cells don't make sense, but obviously he has a vested interest. But no, I think it's going to be a mixture of the two, depending on application and depending on how you want to get power to your system.
Okay. Thank you. Question from Tony here. I assume all fuel cells have a shelf life. Is there investigation going on into recycling and reuse and reduction of waste as part of the projects?
Yes, yeah. So you're right. There is a shelf life. There's current targets from EU, Japan, and the United States, which are the three main people in the policy area, to operate around 150,000 miles in an automotive application. And we're not far off that. There is degradation in the fuel cell that we need to mitigate, and we're doing a lot of work into that. Excuse me, but on the recycling point, fuel cells are actually in a better position for recycling than batteries because, as I was mentioning, everything's kind of sealed within a battery. It's incredibly difficult to take one cell out of 7,000 cells in an electric car, take that cell to pieces and start trying to get some of those materials out. You have to put a lot of energy in. You have to have molten salt at 1,000+ degrees to kind of strip everything out. Whereas with a fuel cell, you just take the fuel cell apart, unloosen the bolts, take one of your cells out, and then you can either take out the individual plastic cell that we showed earlier, take that out and put a new one in, and you can even melt down the material to try and get the precious metal, the platinum, back out. So on a recycling front, fuel cells make a lot more sense than batteries.
Thank you. You talked a lot. You talked towards the end about the industrial partners that you work with, and obviously that's part of your role with UCL East. Could you say a little bit more about how you're working with them towards the goal of decarbonising technology development? Yeah,
so we're working in various ways, from individual sponsored projects. So if a company is very interested in a novel technology, we can look at doing individual projects with them, all the way up to strategic partnerships and companies that, as I mentioned, know they have to make a change. They're going to have to make a big step change, a scary change from market dominance in internal combustion engines, or if you're a testing company, market dominance in testing internal combustion engines. And we are in a prime position to help those companies reevaluate their trajectory. And because of our knowledge and our position as not only a world top 10 university institutionally, but also our kind of high profile we've built in the electrochem storage space and advanced propulsion space, we can help from a variety of small scale projects all the way up to kind of high TRL, ready to roll out commercially scale projects.
Okay. Very good. Question here, has the lockdown impacted your work at APL, and what will be the next research projects once the restrictions ease?
So the day-to-day operation of the lab has been impacted. We can't have people going in unnecessarily. Fortunately, we have a lot of modeling capability. So experiments we've already done in the past, or items we've already scanned, or even just theoretical models can still go ahead. So with remote teaching and remote access, we have a very strong research team on the modeling side. And interestingly enough, because of these changes in industry, a lot of people start with the modeling scale. So instead of actually putting a lot of money into putting a new fuel cell or battery system into a vehicle, they'll model that theoretically first, run it through simulations, make sure everything makes sense, the sizing's right, and so forth. So the modeling capability is carried on. Experimentation has taken a hit, but APL is still productive. I think if you look at UCL East entity output, APL are still publishing papers. Before the facility is even built, we're using a lot of our capabilities that we can do without the building. But then when the building does come around, which I think construction has not hindered the APL building, well, the Marshgate building at UCL East where the APL will be. So in that context, we're still on target. And when we get the keys to the doors, we will upscale our activities.
Okay, very good. This is interesting question. It's always a good one. So how did you get into this research?
Me personally, so this was, like I say, this is my 10th year. So I've started thinking about it a lot. And I'd left a master's in climate change. I've just done a climate change and sustainable development master's. And I've always had this personal drive to eco-friendliness and green warrior kind of stuff. I've got, everyone's got their vices, and I've dabbled in internal combustion engine driving and whatnot. But I wanted to do something that I thought was going to be impactful. And the fuel cell industry, or the fuel cell research community, has always been saying since I started my PhD 10 years ago, that this is the next thing. This is going to be around the corner in the next couple of years. Fuel cells will be the big thing. So I've been having that for a decade. But unfortunately now, it's actually happening. There's policies going in place. There's funding set aside by government. I drive around London in a fuel cell car now. It's all taking off. So all the hard work over the past 10 years is starting to pay off.
Good. There's a question here about when APL will start to operate. I guess it already is, but could you say something about how the ramp up and expansion into UCL East will enable you to start new things?
Yeah, so as I mentioned, the APL is starting to have some output now on what we can do now. But then the actual building is going to be operationally ready in 2023. And by that time, we're hoping to have secured a lot of industry partnerships, which can have some overlap anyway. There's people we work with that have some facilities of their own that in the short to medium term are viable. And some of the stuff that we do in Bloomsbury's immediately worthwhile undertaking. But as we ramp up, we are taking on more projects, bigger projects. So normally when we do EPSRC or Innovate UK projects, we can now start looking at the shift towards Innovate and APC projects, which means Advanced Propulsion Centre, which is higher TRLs, bigger budgets, bigger systems. But ultimately, the APL is at this stage now where we will react and work alongside any interested parties that want to come and support our activities, where we bring the knowledge and we bring the prestige of what we're doing. And then if we can leverage funding from direct investment from industry or from government pots, then we kind of shape what the APL becomes from that.
Good. Maybe just a final one for me then. I mean, you talked about the group that is doing this work, and a large group of people are obviously involved in this. There might well be sort of potential students, people considering coming to study at UCL, watching this. Could you say a little bit about how students, whether it's at undergraduate level or master's level, are involved in this research?
Well, yeah, throughout this is ultimately about training the next generation of engineers in these areas. So it's at the heart of what we do. And we've already started taking on some people to work on APL-related projects. So they are starting now PhD projects or master's projects, working up to the facility opening. But ultimately, everything that we want to do at APL has this academic line going through it. even though it will be more industry facing, we're bringing students into projects where the projects themselves are more industry focused, but the academic integrity is still there. Because ultimately, this field is still in its infancy. Companies still don't understand fully how to implement battery electric or fuel cell electric vehicles from the fundamentals all the way to the systems. So yeah, we're bringing students in on projects with our partners to accelerate activity towards opening the doors in a couple of years' time.
Thank you. I think that's a really important point that our next generation of graduates are going to need to know about this technology and how they're integrated in all the applications that this could possibly serve. And so this is a place for them to learn that right from the technology that is going to be out there in 5, 10, 15 years time is going to be vital. So thank you ever so much for everyone for joining us. Thank you very much to Mike for an inspiring and enlightening talk on the work of the APL. If you wish to know more about upcoming lectures, please visit the UCL Minds website, which has a full list of all the topics that are coming up. And thank you all very much. Have a good day, and hope you all stay well.